Chapter 10 in class exercise 1. Determine the moment of inertia of the beam's cross-sectional area about the centroidal axis x and y. So we have this like hollow rectangular beam and we would like to calculate the moment of inertia of this beam about x and y axis. Remember that for solid rectangular shape, if it is like single solid shape and that has width b and height h, then the formula for moment of inertia about x is 1 by 12 bh cube, and for y it's 1 by 12 hb cube. Now, but we don't have a single solid rectangular shape, but we have a hollow rectangular shape. Now what we can do is we can use concept of composite shapes and calculate the overall moment of inertia by first calculating the moment of inertia of the outside box, outside rectangular shape, minus moment of inertia of this inner box. Because this is hollow, we need to do subtraction for the inner shape. So it's outside minus inside for both x and y gives us the overall moment of inertia. And for each shape, we can calculate moment of inertia using this formula. So for outside, it is 1 by 12 and the width is 360 millimeter and height is 200 millimeter cube. And for inside shape, it's 1 by 12. I'm talking about the IX. For inside shape, it's 1 by 12, 300 multiplied by this height from here to here. And this height from here to here is 200 minus 60, which is 140 millimeter. So yeah, it's a very simple problem. So let's apply those equations here. So for outside shape, it's 1 by 12, 360 multiplied by 200 cube. This is for IX, minus negative because it's hollow, 1 by 12, 300 multiplied by 140 cube. And the final answer is this number. Unit is millimeter to the power 4. And same applies to y-axis, but the cube is now different. Now it's hb cube. So hb cube for outside rectangle minus hb cube for inside rectangle, and the total moment of inertia is 463 multiplied by 10 to the power 6 millimeter to the 4. Okay, so it's a very simple concept, it's very simple math. If it is composite, if its material is added, then we add moment of inertia of individual shapes. If it's hollow, then we subtract the moment of inertia of individual shapes. So let's still look at one problem where we need to do addition of different shapes to get the composite shape area moment of inertia, and that's this I section problem. Okay, so for this problem, determine the moment of inertia about x-axis and y-axis for the I section. Now the overall x and the x and y-axis are defined to the with respect to this overall centroid of the I section, which is here. So that's x-axis, this vertical is y-axis. We can define, so this rectangle 1, 2 and 3 cross section, for y moment of inertia, y-axis passes through centroid of each shape. So this is C1, centroid of top rectangle. C2, centroid of middle rectangle is same as the overall centroid. And C3 is here. Since y-axis, you can see here, it passes through centroid of all individual shapes, we can directly add the moment of inertia of shape 1, shape 2 and shape 3 to get the overall area moment of inertia about y-axis. So that's what is given here. So for y-axis, the moment of inertia is shape 1 plus sorry, this is shape 1 and 3 plus shape 2, and that is millimeter to the 4. Now if you look at this number here, the number says 360, 1 by 12, 360 multiplied by 20 cube, which is 360 is this distance here. So this is 200 minus 20. So this gap from here to here is 360. You can check with the dimension, and this is 20 cube. So this term 1 by 12, 360 multiplied by 20 cube is the moment of inertia of the middle shape, plus 1 by 12, 40. Now see, this is 20 and this is 20. So here both of them are added together and the moment of inertia is calculated as 4t multiplied by 300 cube, where 300 is this distance here, and that's the overall moment of inertia. Okay. For y-axis, because y-axis passes through all the individual centroids, we can directly add or subtract them. Now we cannot do the same for x-axis, because if you look at it here, the x-axis for shape 1 centroid is here, ix1. For shape 2 is in line, which is ix2, and for shape 3 it's here. So we need to apply parallel axis theorem for ix. Means we calculate the moment of inertia of this shape about ix1, and then using parallel axis theorem, we calculate the moment of inertia about x-axis. Same we do for the shape 3, and then for shape 2, we can directly apply the formula because the centroid passes through x-axis of interest. Now that is being given here. This is one way that we can do parallel axis theorem, or another option that we can try. Let me copy and paste it here. Another option that we can try is we can find out the moment of inertia of the outside big rectangle, which is about x-axis. So ix for the big shape, outside shape, let's call the shape 1, is equal to 1 by 12 bh cube, which is 1 by 12, and b is 300 and h cube is 400 cube. Minus, we subtract these two small rectangles. This one on the one side of I section and this one on the other side of I section. So it's minus, okay, that's for the outside shape 1. And for shape 2 is just these two rectangles. So we find ix2 using the same 1 by 12 bh cube, and then later find the overall moment of inertia of the I section about x-axis by subtracting shape 2 from shape 1, because we are removing material. So it's 1 by 12 C300 400 cube minus 1 by 12 280 minus 360 cube. So this 280 minus 360 cube, where 280 is actually the width of this rectangle from here to here plus width of this rectangle. This is 150, and the width has, like, this is 20 millimeter here, so half of that is 10 millimeter, means from one end, let me draw this here, from this end to this gap is 140, and from this end to this corner, that is also 140. So 140 plus 140 is 280. That's why we have 1 by 12 280 multiplied by h cube, where h is this height from here all the way up to here for the middle rectangle, and that's 360 millimeter. And then this is the overall moment of inertia of I section about x-axis and about y-axis. Thank you.